All right. Hello, everyone. This is going to be a technical walkthrough video with Sam from the execution layer specification team. So in this video, the execution layer touches a lot of the clients who implement, obviously, the execution side of the EVM and the Ethereum protocol. So this is going to be a very important video to watch to get an idea of what kind of functionality all of these clients are implementing. So yeah, I'm going to let Sam take it away here and give you guys a walkthrough of the repository.
Sure. Yeah. So hi, I'm Sam. I'm with the Ethereum Foundation, and I'm generally responsible for EELS, otherwise known as the Ethereum Execution Layer Specification. You may have also seen me around the EIPs and ERCs repositories. That's kind of another area that I work on. Basically, if it has something to do with the execution layer specifications, you'll probably find me there. So I guess I can talk a little bit about what EELS is and how it's structured at a high level, and then I'll give you a walkthrough of getting it set up, and then we'll dive through some of the code and how it's structured. So yeah, so what is EELS? So short definition is that it's a reference implementation of the Ethereum execution layer. So in more practical terms, that means we're a Python library that takes blocks in RLP format from an existing execution client, can process those blocks from like decoding transactions, putting them into the EVM, running the bytecode, and then updating the state database. We've actually managed to sync all the way from Genesis up to about block 18 million. So we're almost caught up finally with mainnet. Yeah, so the goal is to provide a framework or a jumping off point for people trying to change the protocol and being able to specify their changes in a way that makes sense. So if you're familiar with EIPs, you'll notice that a lot of the older ones are written as like an English description of the changes, and a lot of time that ends up being very ambiguous or difficult to understand. So EELS's goal is to make those changes like very well defined, kind of like as a Python patch. So we provide like the base framework for people to write their changes for the protocol. And then the consumers of EELS are core developers and people who are interested in the protocol itself. So the kind of intended workflow is EIP author comes along, makes a proposal, changes EELS, presents those changes in an EIP. And then if that EIP is accepted, core developers can look at the patch and make those changes to their execution clients. There are a bunch of things that are out of scope for EELS as well. We don't deal with consensus. We don't deal with rollbacks or any of that. We assume that every block we get is the canonical chain. And there are a few other simplifying assumptions we make. But I mean, that's the big one. So yeah, what else? Yeah, okay, so I guess we'll talk about kind of the structure. So because we want to be a very understandable project, EELS is structured into forks, where each fork is the entirety of Ethereum at that fork. So if you're more familiar with traditional clients, you'll find like there is one apply body function, let's say, and it'll have conditionals depending on what fork you're in. We don't do that. Our style is to have each fork be entirely self-contained, and we'll get into that a little bit more later on. Yeah, so I guess let's get started setting up, unless you have any questions for me before I get into that.
No, I think that was a great overview. I think we can get into the
okay.
story. Yep.
Cool. So where is my browser? There you are. Okay, so yeah, we're Ethereum execution specs. We're pretty easy to set up. Regular Python project. So let's get into that. So you can just clone that. All right, I guess I can talk a little bit about our supporting libraries too. So execution specs is the main project where you'll find most of our code, but we do also have some supporting libraries. The next one here is Ethereum types. So we'll get a copy of this as well, and we'll clone that. It's not necessary to clone it, but I'm going to walk you through it later, so we're going to grab it. Those are the two main ones. Yeah, so let's just dive into it. So we support any Python version greater than 3.0. And you have to start off by creating a virtual environment. So if you're not familiar with Python virtual environments, they're kind of like a self-contained area where you can install packages and it doesn't affect the rest of your system. So the way you do that is with python-m venv, and then the name of the virtual environment you want to create, and it's traditional to also call it venv. Then you activate your virtual environment. Activate. So now we're in the virtual environment. You can see it over here in our prompt. Now let's go into execution specs. So there are a lot of folders and directories in here. Some of them are historical, like network upgrades is a list of markdown files. You can ignore that entirely. Same thing with lists. Most of the stuff you're going to be looking at is going to be in source and tests. So let's get this project installed. So let's do lint, doc, test. I think those are the big ones. There might be also tools. So I'll explain what this command does here. So pip install -e means install this project into the current environment. The -e means in editable mode. So changes you make here will be reflected when you try to execute the program. And then all of these little sections here are optional things that you can enable. So we'll be enabling the linting, the documentation generation, the testing, and the associated tools. This does require Rust. So if you don't have Rust set up, you'll need to set that up first. There are also a few other libraries you might need to grab, like OpenSSL, but that's all documented in the README, hopefully. Yeah, so let's continue on from here. So now we have it set up. So if we jump into Python, you go from Ethereum, import, say version. And that's how you know the specs are installed. So what else can we do here? So not that I expect people to be modifying the specs that much as part of the this process, but if you do want to make a PR, there are a couple of requirements that we have. So we use Tox. So let's get that installed. Tox is a kind of like make or auto tools, if you're familiar with that, but for Python. So tox-e static will run our static analysis tools. As long as this passes, you're generally pretty good to open a PR. So we'll let that run.
And what are some of the other advantages of installing this tooling for going through the code base for the execution layer?
Sure. So the reason why I like setting it up is it also enables your language server. So I use Jedi, and having it all set up lets you jump around and navigate the code a lot easier. So once you have this working, it makes navigating so much simpler. And I guess we can jump into that now.
Okay, cool. Yeah, no, that sounds like a really great advantage. Yeah.
Yeah. So please excuse my broken fonts, new computer. But so this is the project opened up in Vim. Let's get that started. Okay, so the fun stuff is all in SRC. So we'll start there. So SRC Ethereum is where the actual specification lives. This is what we're most concerned about for bug reports and vulnerabilities and everything. So if you're going to look somewhere, start looking here. We also have a kind of a monkey patch called Ethereum Optimized. So when we're actually syncing the chain for real, the the Python implementation is often not fast enough. So we swap out bits of the Python implementation with Rust. So this area is a little bit less interesting from a vulnerability or bug point of view, because it's just supposed to do the exact same thing as SRC Ethereum, just faster. Not that interesting. And then finally, we have Ethereum spec tools. So this is where most of our supporting kind of tooling exists. Our documentation generator, some of our linting tools are in here, and the tool that actually like syncs the chain is in here. But these are kind of alongside the specification. Obviously, we appreciate bug reports for this as well, but it's not like our core product. This is just like helpful tools. So yeah, let's jump into the actual meat here. So you'll notice inside of SRC Ethereum that we have a bunch of folders that are named after forks. So for example, you have Frontier, Homestead, all the way up to Cancun. We also have the Prague fork implemented. It's in a separate branch. Bug reports are welcome for that too. It's just a little bit newer and less stable, I guess. So might be more fun to look there if you're just looking for easy fixes. But yeah, okay. So let's start with Frontier. So actually, let's start with even more high level. So we have kind of shared code and not shared code. Things here like, for example, crypto. This is shared among all forks. And so it's not in a fork folder. You also won't find it repeated over and over again, where you will with the other folders. There are a couple things like that. There's also what am I looking for? Utils, utils that contains things like parsing, hexadecimal strings, stuff like that. We also have our implementation of ETH#, the Genesis configuration. So this loads like the initial allocation of ETH in the Genesis block and all that. We also have RLP. So this is a fun one that probably needs some attention. This file defines the encoding and decoding from Python objects to RLP byte sequences. It's kind of messy Python, and it's probably really buggy. So yeah, definitely take a look at this file. Trace is kind of how we integrate with the T8N tooling and the testing and the fuzzing. So this file contains like how we emit events for, like, this is the beginning of the jump opcode. This is the end of a transaction. So all of that is done through the trace file. What else is in here? So fork criteria is kind of like when does a certain fork activate, either by block number, by timestamp, or we don't know yet. So that's defined in fork criteria. Yeah, so that's the main ones there. So again, crypto contains our crypto implementations. Most of them are lifted from Coin Curve, but some of them are implemented ourselves. Like what's it? Is it KZG that's implemented ourselves? No, like one of them. Anyways, we've implemented some of our own crypto algorithms, so probably another area to pay attention to. Yeah, so I guess let's dive into a fork here, and we'll go from there. So every fork is organized the exact same way. So you'll see every fork has the same modules, the same layout. In fact, you can basically delete an entire fork folder and all the other forks will keep working because they're completely separate from each other, with some caveats. But yeah, so the entry point for each fork is fork.py. And this is where all the magic happens. So each fork defines its version of the blockchain as a list of blocks and the current state, as well as the current chain ID. When each fork begins, so like at the transition between, let's say, Frontier and Homestead, the apply fork function would be called. So the DAO fork is interesting for apply fork because it actually does something here. So it calls the apply DAO. So you can see here, these are all of the addresses that get their balances adjusted as part of the DAO fork. Yeah, so where is the fun one here? Yeah, so state transition is the core function of the fork. So after apply body has been completed, each block that the specs receive goes into the state transition function. And you can see here all the checks that happen, right? Like it checks the header, it checks the omers, and then it applies the body of the fork, checks the gas, checks the transaction and the state roots, make sure all of that's correct. And yeah, that's it. This function just gets called in a loop over and over again for each block in the fork. So this is probably like the entry point where you should start looking for interesting things. Yeah, so again, validate header and yeah, so that's pretty much it for this. The more interesting stuff is in the VM. Well, before we get into that, so we have the definitions for the block types. So that's in blocks. The definitions for transaction types are in transactions. I think that's pretty self-explanatory. The state database is in state.py. And the code for generating tries and roots and everything is in try.py. So hopefully that's all pretty easy to navigate. So utils has fork-specific utilities. So for example, if you want to convert hexadecimal into the fork's address type, that's going to live here in hexadecimal. Yeah, so that stuff is mostly just encoding and decoding utilities. But we can go into VM here. So VM is the VM. That should be obvious. Interpreter is kind of the, I think it's, is it a init or interpreter? Yeah, okay, so it's interpreter. So interpreter is where all of the magic happens for executing the EVM. So where's my stack here? Stack? No, that's that one. Okay, so the EVM is represented as a like call stack of EVM objects. So EVM is kind of like the state of a particular layer or level of execution. And then each one has a message inside of it, and a message represents like the information regarding the call. And then you have the environment, which represents the block number, the tx.origin, all that kind of stuff. So with these three classes together, you can implement the EVM. Yeah, so I guess let's show you an example of an instruction here. So control flow, I guess, would be a good one. So each EVM instruction is divided into 4 parts. So you have a regular Python function, and then you have the stack manipulation section, the gas accounting section, actually processing the instruction, and then finally you have what are like modifications to the program counter. So that's repeated for every single opcode that we have implemented. So here you'll see the jump, which is very similar. It pops the jump test off the stack, charges gas, checks for valid jump destinations, and then updates the program counter to the jump destination. And that's no matter what type of instruction you have. Like if we go into memory, you'll have mstore, the exact same pattern, stack manipulation, followed by gas accounting, actually doing the opcode, and then manipulating the program counter. All of the instructions are organized inside of the init file. So this contains the mapping from the actual machine representation to the human name, and then from the human name to the implementation function is also defined here. So some things to pay attention to here, things we've had bug reports about before, are the order of warming addresses is a big one. So in later forks, there's the idea of warm and cold address accesses. That's something to pay very close attention to because it can kind of screw up gas accounting, and we don't have very good test coverage for that area. So yeah, just make sure that when you warm an address, it's warmed at the right point in the instruction implementation. Yeah, a lot of the organization of the opcodes themselves is lifted from the yellow paper. So the way that they organize their instructions is kind of the way we organize them here. Yeah, and then I guess we can talk about this. So here's kind of the main loop of the interpreter. So yeah, it just grabs the opcode and then executes the opcode, and it does that in a loop until it hits a stop or runs out of instructions to execute. So yeah, that's kind of a high-level overview of everything. And just to reiterate this, every fork has exactly the same files with exactly the same. Where are we here? Yeah, with the exact same code. So like, it's kind of a pain to work on this, but like when you're reading the code, it should be very understandable and easy to navigate. Yeah, so I guess that's it for a very high level kind of overview of this. Did you have any questions? Did I go too quickly over anything? Yeah.
This is really interesting. I think something I wanted to cover here is, the execution layer specifications here, they are codified and written in Python, but it's not necessarily a client itself. Right.
Yeah, it's about like half a client. So it doesn't implement networking. It doesn't implement like rolling back from the head of the chain if there's like consensus issues or anything like that. It just assumes that the blocks it receives are like the canonical chain. But after that point, it's a full client.
Okay, great. So if there is a bug that you find though in the specification layer, it's likely something that affects every other execution client which has been implemented.
So I guess there's two classes of bugs, and this is something we went over when we were trying to figure out the severity levels for EELS. So there are bugs in like the theoretical design of Ethereum, and those would be bugs in other clients as well. And then there are bugs where EELS doesn't match the theoretical specification of Ethereum. So like, if you find a bug in EELS, like let's say we don't warm an address at the right place. Sorry, we've been dealing with that a lot. That's why I bring it up again. So that, like, to determine whether it's a bug in EELS or like in Ethereum as a whole, you'd want to compare EELS's implementation with, say, Geth or Besu or another client. And if it's implemented the same way in EELS and in this other client, then it's likely a very severe bug in Ethereum itself. But if EELS differs from the implementation of a client, then it's a bug in EELS, and that's a little bit less severe. Does that kind of make sense?
Yeah, that makes sense. That definitely clarifies what I was asking about. Cool. Yeah. So you can definitely find errors in translation in clients themselves, but those are more related to the client. And then you have these bugs that are related to the Ethereum specification layer, which may not necessarily affect the network, but is still something that you guys are interested in finding.
Exactly. Yeah. Okay. So like, yeah, there are bugs in every client, like including EELS and Geth and whatever, and though like that's like a bug in Ethereum itself, and then there are bugs in EELS's representation of Ethereum, and that's like a less severe thing. Yeah.
Okay, I see. Great. Awesome.
Yeah.
Thank you for that clarification.
Yeah, my pleasure. Yeah, so I guess that's it for me, really. I guess I can show you a little bit of the tooling and the tests because that's kind of important. So okay, so if you're familiar with how Ethereum testing works, There are several tools that are used to generate and fill tests. So the idea is you specify a test in Python code in the execution spec tests repository. And you do things like send transactions and verify like storage slots after. And then the execution spec tests takes that Python code and runs it against a client. And it captures the inputs and outputs as a series of JSON files. So all of that is handled by the T8N tool. Yeah, and then those JSON files are then consumed by EELS and other clients. And that is done inside the tests directory. So like if you're looking to do like a 110% effort and you want to do like the best possible bug report, then writing a test in execution spec tests and then filling it and then demonstrating that two clients don't behave the same way, that's like the gold standard for a bug report against EELS. The other tooling we have is pretty lightweight. We have some linters and some documentation generating stuff. Don't really pay attention to that. It's not important enough to get bug reports. But yeah, that's it. That's pretty much all of the scope and tools and code and yeah. So
cool.
Thank you for.
I did have one question here. I did want to come back to maybe what, in your opinion, is the most complex functionality that you see in here. Maybe what like a lot of some area where you had to have a lot of tests for, or an area where it might not have as much coverage as you feel it should.
Sure. So I can talk about that kind of separately. So the most complicated part by far is the EVM. Like that is, there's so many moving parts and so many little edge cases for each opcode. And the test coverage is decent, but it's not excellent. Like for example, like there's the block hash opcode, and it doesn't have, there are no tests that test whether, the 255th versus the 256th block hash are correct. So really digging into individual opcodes and trying to like break them or find differences between EELS and a real client. That's a great area for it. Yeah, so what was the other thing I was going to say? And an area with absolutely zero test coverage in EELS, that's not true of other clients, is the transition blocks between forks. So for example, like we don't have any tests that cover what happens if there is an Omer block in the immediately preceding a fork, or we don't have any tests that verify whether the DAO fork actually tests what it's supposed to. So poking around the transition blocks would be a great place to investigate for bugs.
Awesome, thank you. Cool. And do you have any tips or suggestions on how to navigate the code base? I know there's a lot here, but do you have any tips or suggestions, like maybe tooling that you use? I know we showed how to install those Python libraries, which allow navigating the code.
Yeah. So I guess the biggest tip I have is don't be intimidated by how many lines of code there are. They're almost all duplicated between forks. So yeah, it's like just pick one fork and look in there, unless there's a specific reason for you to look at more than one fork, because it's all going to be the same. That actually leads to another good point. So part of our tooling is to generate. Is that going to work? Yeah, okay. So we generate diffs between forks to kind of highlight the differences. So for example, this section here is the diff between the DAO fork and Tangerine Whistle. So if we go into, let's say, fork.py, we actually generate like basically like patches that highlight the changes between forks. So if you're unsure of like what has changed between forks, our documentation actually is pretty useful for finding that. So you can see here, like in Tangerine Whistle, we remove the apply DAO call. Yeah, so this is on ethereum.io/execution specs, and you can kind of find all of the fork changes here. This is how I kind of navigate when I'm looking for like a particular EIP, like what the implementation is. This is the website to use for that.
Super cool. This looks very useful. Awesome. Okay, and I think my last question for you then is where can security researchers learn more? And do you have maybe a community researchers can get involved with to ask some more questions?
Yeah, definitely. So, I mean, reading EELS is probably the best way to learn EELS itself. But if you want more of like an academic kind of background, the yellow paper is a great resource. If you're not familiar with it, like go and read it before you dive into EELS. It's a little bit dense on like notation, but once you get past that, it's pretty useful. And as for our community, yeah, so we have a decently active community in the ETH R&D Discord under the specification section. Feel free to tag me if you want like a faster response to your questions. I'm Sam Wilson, but without the O. Yeah, just feel free to @me and ask anything you like.
Okay, awesome. Thank you very much. I think we can wrap up here then. If there's any last words from you, Sam, that you want to say here.
You know, I really appreciate any bug reports that you have. Like, I mean, we're like 4 years old at this point, but it still feels like a new project. So if you have problems setting it up, you have like issues navigating the code, just reach out, let us know, open an issue, and you know, we'll be happy to help. And you know, thanks for taking a look at our code.
Sweet, awesome. Thank you so much for your time, Sam. Really appreciate the great overview here.
Oh, it's my pleasure. Thanks for having me.